In this video, we're going to talk about limits at infinity. So just as an overview, limits at infinity are really helpful for us in mathematics because it kind of describes the long-term behavior of a function. So if this x-axis continues all the way to infinity, what is the y value that I start approaching? And in this particular graph, it's approaching 4. And what's interesting about that is 4 is actually a horizontal asymptote of this function. And horizontal and vertical asymptotes, when we talk about limits at infinity, are really important. Not even really the vertical, but the horizontal ones, big time. So this is the concept that we're going to take a look at. So here we have a function that's doing a whole bunch of different stuff, but the blue horizontal lines are our asymptotes, and the orange line is basically just our function. And we're going to ask ourselves a couple different questions. Where is this function going as we approach infinity, and where is it going as it approaches negative infinity? And if we carefully follow our graph, when we approach positive infinity, I'm going to be looking at this part at the top, and it's going to follow along that x value forever. It is an asymptote of this function. So where does that asymptote happen? It's at 1, 2, 3, 4, 5. So my limit as I approach infinity is 5. So when we take a look at negative infinity, we're going to do the exact opposite. Instead of going to the right, we're going to go to the left. So if I go towards the bottom of my graph and start tracing along this, it will follow that asymptote all the way until it gets to negative infinity. And that is at negative 3, and that's going to be our limit. So let's take a look at a couple more. So this is our parent function, e to the x. And we're going to take a look at the limits as we approach infinity and then negative infinity. So I'm going to start with positive infinity first. So I'm going to trace along the right-hand part of my graph. And this is actually just going to continue going up and up and up forever. So this limit is actually infinity. Now when we take a look at the left-hand part, when I'm approaching negative infinity, there is an asymptote over here, which is the x-axis, which is y equals 0. So my limit as I approach negative infinity is going to be 0. So along with this, we actually have a theorem that states a couple rules for us. So we're going to talk about some basic functions as long as n is greater than 0. So we're talking 1, we're talking 2, 3, any of those things. So we are going to have a rule for this first one right here, in that if we have the limit as x approaches infinity of x to the n, no matter what it is, it will always approach infinity no matter what. The other rule that we have is the limit as x approaches infinity of x to the negative n, or 1 over x to the n. And that's always going to be equivalent to 0. And that actually makes a lot of sense because the bigger this is, the smaller that fraction becomes. So that's why we approach 0 in that case. Now in this next one, this guy right here, if the limit as x approaches negative infinity of x to the n, so this is with negative infinity, we have two different cases. If my function is even, in other words, x squared, x to the 4th, x to the 6th, if we have those kinds of functions, then our limit will approach infinity. If it's an odd function, like x, x cubed, x to the 5th, etc., then we actually approach negative infinity. The other case is down here at the bottom. The limit as x approaches negative infinity of our fraction is also going to be 0 because, again, it doesn't matter really how big that gets. If it keeps getting bigger, even though it's negative, that fraction is going to get closer and closer to 0. So that's going to be really helpful. The one particular kind of a function that's going to have to be really specific about is the rational functions. So rational functions are very tricky because they typically have zeros, they have holes, they have horizontal asymptotes, they have vertical asymptotes, they have a whole bunch of different stuff that can be going on. So what's really nice about this is we have some rules that have to do with the leading degree, which would be like this guy here and this guy here, and the way that they relate to each other, and then we will automatically always know what their limits will be. So let's start this off with a case where those exponents are actually equivalent to each other. So here's an example. We have 3x to the fourth minus 7x plus 9 divided by 7x to the fourth minus 4. So if we happen to have this particular case and the leading degree of the numerator is equivalent to that of the denominator, the only thing we have to worry about are the leading coefficients. This guy 3 and this guy 7. And what this rule says is that the limit will be that ratio. That's it. So if you can understand that property, and of course this is limits approaching positive and negative, but if you see that those exponents are the same, you can jump straight to the ratio of their coefficients, and that is awesome. We have another case where n would be less than m. So we're going to use the same exact problem as before, except that I changed the fourth power on my 3x to a cube. So this is a case, sure enough, that this n is less than this m. Now, if you happen to have this case, no matter what, your result, as long as you're approaching infinity, will always be 0, no matter what. So that's your second rule. So here's our next rule if n is greater than m, or if n minus m happens to be an odd number, like this case, 3x to the 8th, blah, 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 divided by 7x to the 4th, blah, 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 right? So this guy is larger than the 4. So if this happens, we can automatically jump and say that it is equivalent to infinity. Now this can change, okay? It may be negative infinity as well. It just depends on the kind of function that you have, and it depends on if you're approaching positive or negative infinity. So this n minus m thing, let's see what that actually is talking about. So if I happen to do 8 minus 4, that actually gives me 3. So if it's odd like that, then you have to go back and assume that this is x cubed. You have to go back to these rules here to see if it approaches positive or negative infinity, which is this guy right here. That will tell you. So you still want to be careful about your final answer, but it should be an infinity of some kind if n is greater than m. Now, in the other case, if n is greater than m and n minus m is even, so if you take a look at this particular example, I have 7 for my top, my numerator's exponent, and then 3. And of course, if I do subtract those, I do get an even number. I get 4. So if I were to take a look at the function x to the 4th, it would still become an infinity of some kind. So you want to keep an eye on that as well. So it's going to be a positive or a negative infinity depending on what you have. So those are our limits at infinity properties, and that will conclude this tutorial.